Hey there, here we go into video number 2 in the lesson 6.2 Euler's method. In this video, we seek to accomplish just knowing how to do Euler's method as a process. So I'm going to go over 2 more examples of that, and then in another video, we're going to go over the concept. I'm going to show you why the formula is the way that it is. Okay, so if we remember the Euler's method formula, it approximates y values of the particular solutions of differential equations. So we get this differential equation. We have no idea what it looks like, right? What its solution is. And we want to figure out what f of 2 is, given that we know that f of 1 is negative 3. We're going to use Euler's method to figure out what the y value is on the solution curve without ever finding it. So we're not going to find the exact y, though. We're just going to approximate it. So remember that Euler's method is the y value is approximately the initial y value, starting y value, plus the derivative at whatever point you're at. So that'd be x0 comma y0 or x comma y times delta x. So first things first, we got to figure out delta x. We're told we're going to use 2 steps of equal size, and we're going from 1 to 2. So the overall width that we're examining here is 1, and that's 2 steps, and therefore delta x is equal to 1/2. Okay, so now we're going to use our formula. So we're going to start out by saying, what is f of 1.5? Why are we at 1.5? Well, remember, we're going from 1 to 2, and we're going to do 2 steps. So we're going to take a stop at 1.5, figure out that approximation, then use it to get to 2. So f of 1.5 is approximately, the initial y value is negative 3. We're going to add on to that. Now we need dy dx. So we need dy dx evaluated at the point that we're currently at, 1 comma negative 3. And we're going to multiply that by 1/2 delta x. So what's dy dx at 1 negative 3? Well, that would be 4 times 1 is 4, minus a negative 3 is 7, because you got 4 minus a negative 3, which would be 7. So this is going to be equal to negative 3 plus 7 times 1/2. So I'm going to write that as a decimal. Why not? So that's negative 3 plus 7/2, or 3.5, is equal to 0.5. So what that means is we're at the point 1.5 comma 0.5. Or 3/2 comma 1/2, however you'd rather roll. So now we're assuming that that point is now on the solution curve. It's not, but we're assuming it is. We're going to go to f of 2. How do we get there? Well, we're going to write a tangent line basically starting at 0.5 plus, and we're going to take the derivative at this point, 1.5 comma 0.5. And we're going to multiply that again by delta x, which is 1/2 or 0.5. Okay, so from here, 0.5 is going to be added on to the derivative at this point. 4 times 1.5 is 6, minus 0.5 is 5.5. So we have 5.5 times 1/2. Okay, well that's going to be equal to 0.5 plus half of 5.5 is 2.75. And so that's going to be equal to 3.25. So f of 2 is approximately 3.25. That's it. Is it the exact value? No, it's an approximation. Euler's method in its finest. So we're going to go over one more problem. Given the differential equation below and y equals f of x is a particular solution, use Euler's method starting at x equals 0 and 2 steps again. That's common, especially in the AB or on the BC exam. It's not an AB topic. So to approximate f of negative 2, it's common to do 2 steps. We're going from 0 to negative 2, so be careful there. We're going backwards. So if we're going from 0 back to negative 2, the overall width is negative 2, right? You're going to the left. It's like doing negative 2 minus 0. So I'll write that all over 2. So delta x is minus 1, right? So we go from 0 to negative 1, then to negative 2. And as always, we're going to use our approximation formula. It's y is approximately the starting y value, y naught, plus dy dx evaluated at x comma y, and I guess it'd be x naught, y naught, if you really want to be fancy, times delta x. Let's do this. So we now follow our formula. It's very easy to plug in. The initial y value is, what's the initial y value? 0, 1. So 1 is the y value, and so we're going to approximate f of negative 1. We're moving over to the left 1 from 0 to get our first stop at negative 1. That's our first step. That's approximately, well, f of negative 1 is going to, well, we're going to get it by starting at 0, 1. And we're going to add dy dx at the point that we are currently, which is 0, 1. And we're going to multiply that by delta x, which in this case is -1. Be careful here with that negative. It's because we're moving backwards in the x direction. Okay, so let's plug it in. dy dx at 0, 1. I'll just do a little side work here. 0, 1, 0 minus 1, all over 1. Well, that's going to be equal to -1. Well, that's not bad. 1 plus -1 is this, times -1, is equal to 2. So what that means is the point that we've arrived at is the point -1, 2. So that's the approximate value on this curve that we don't know is f of -1 equals 2. So how do we get to f of -2? We do it again. Do it again. Nice. So we're going to start at the value of 2 plus, got dy dx at the point that we are now currently, -1 comma 2. And we're going to multiply that by, delta x, which is -1. And now we plug into the derivative again. So that's -1, 2. Don't let this notation scare you. It's not that bad. -1 comma 2, we plug it into here. So dy dx would be -1 minus 1, x minus 1, all over 2, which again is -1. Well, that's pretty. Real simple. 2 plus -1 times -1. That's 2 plus 1, which is 3. So therefore, we have the point -2 comma 3 as an approximation. So f of -2 is approximately 3. Another Euler's method approximation. It's beautiful. Now, if you're looking at this and you're like, okay, I've got the process, but why is this function? Why is it that function that works that way? Then you need to check out the third and final lesson video here. I'm going to go over why this function makes sense. And I can't wait to see you there. But until then, always, 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 be well in peace.